Hello, today's lesson we're going to talk about the basics of doing the opposite of taking a derivative. Surprisingly, the opposite of derivative is called the antiderivative. Simple enough. The notation goes as this: if the derivative of a function equals, or if derivative of x squared is equal to 2x, then the antiderivative of 2x would be equal to x squared. Notice here, I'm having f of x. It's not a derivative, that's a normal function. If I differentiate, then I get f prime of x. But if I anti-differentiate, then I get the big F. And that equals x squared. So just some very basic ones. If you have a function whose e to the x, then the antiderivative is surprisingly e to the x, because the derivative of f of big F is little f. Good to go. Now again here, the derivative of f of x would be 3x squared, but we're going to go the other way. So this is going to be a power higher, so it's going to be x to the fourth. And then we have to remember that we're doing the opposite of differentiating. So we used to multiply by the exponent. Now we should probably unmultiply, which is known as dividing. If you were to check this one and differentiate big F, you're going to have 4 times a fourth, which is 1, and then you'll have x to the fourth becomes x cubed, so we're good to go. Try to use the same technique here, and you'll fall short. You have to remember that the derivative of the natural log of x is 1 over x. So this one has to come out of memory, but you'll try, if you use power ruling, you'll find it falls apart here, and that's for a different lesson. Anyway, the antiderivative, the derivative of the cosine is a negative sign. The antiderivative of the cosine should be positive sign, and again, you're going to probably be unsure about that, but if you differentiate sine of x and you get the cosine of x, that's how you know you're right. So this is some of the basics. I just want to look at some examples of some functions just so we can see kind of how it all pieces together. Here, if dy dx is 3x squared, then y, the antiderivative, we're going to raise the power by 1 and then divide by that new power. So it's going to be 3 times 1/3, which is 1, so it's x cubed. Which, again, take the derivative of x cubed, you get 3x squared. So it's not really that difficult to see. Here, before we do this, because I'm afraid of quotients, I'm going to make this negative x to the negative 2. Now when I antidifferentiate, this is the tricky part. I got to remember the power goes up by 1, not down. And up from negative 2 is negative 1. And so we're going to divide by that new exponent, divide by negative 1, which is why we have positive x to the negative 1. If I take the derivative of... Oh, yeah, sorry. I've lost my train of thought. Yeah, if I rewrite the derivative, I get negative 1 over x squared, which isn't really checking my answer at all. What I meant to do was to take the derivative of... Oh, no, I did do it. Never mind. Take the derivative of this, you get that. It's so easy, I forgot it was there. All right. This one, same deal we talked about before, where the derivative of the derivative of the natural log of x is 1 over x. So the antiderivative of 1 over x is going to be natural log. Well, this is a modification of 1 over x. It still follows the same general rules and behaviors. We're just going to have 4 times as much, and it's going to be shifted over a little bit. But it still follows the same differentiation rules. And you can check it because if you take the derivative, constants aren't affected by derivative, and boom, we get what we came from. And last but not least, of course, we have y equals the opposite of 2 sine of x if the derivative was the opposite of 2 cosine of x. Always check, take the derivative of the sine of x, it's cosine of x, so the negative 2 carries. Looking at any of these, sometimes the checks are just by taking the derivative back again, but a lot of times you'll make the same mistakes in both directions. So you want to have some technology available to make sure that you're not making any bonehead moves. So for example, you could always go to Desmos, and looking at this one, we have the dy dx, the given function was 4 over x minus 1. So when I go to Desmos, I can see here we have y equals, not dy dx, because Desmos doesn't support that. But we have y equals 4 over x minus 1, and then I have what I got as my answer, 4 times the natural log of x minus 1, and then I asked Desmos to differentiate my answer. If I did everything right, then these two graphs should be the same. That is f prime of x, and the given function should be the one and the same, and in fact they are. So that's a way you can check electronically. Last thing before I finish up this here video, just want to mention sometimes antiderivatives really are just a matter of just the opposite of your thinking, and it's not that hard as long as you remember how to differentiate. Sometimes, however, and this is just to illustrate that fact, things that look like they might be simple to anti-differentiate turn out to be kind of tricky. There's little tricks involved. For example, the tangent antiderivative is the natural log of the secant. Where does that come from? And the antiderivative of the natural log is actually x natural log of x minus x, and the weirdest part here is this has no trigonometry in it whatsoever, or it doesn't look like it does, but its antiderivative is actually an inverse tangent, if you can believe that. So anyway, those are some examples that not all antidifferentiation is a piece of cake, but we're going to work with some of the basic steps and figure out what antiderivatives are good for, but now at least we have this lesson to demonstrate some of the basics. So hope that's helpful. Thanks for watching.